Welcome to my first attempt at making a video PowerPoint Year 12. Here it goes. This is on torque and equilibrium. So you've had a look at what torque is briefly. It's a turning force. It's created when a force is applied at a distance a certain point from a pivot or a fulcrum, and it causes an object to turn or to spin. So in the diagram below, we have a weight on the end of a beam, which is a certain distance from the fulcrum. Obviously, if that was let to drop, it would cause the beam to turn around to the right. That's called a clockwise torque because it turns the beam in a clockwise direction. The equation for this, if we haven't come across it already, is force times distance moved. In this case, it says Fg because it's the force created by gravity. In general terms, torque is measured in Newton meters, and the units come from the force in newtons multiplied by the perpendicular distance to the pivot. In this case, it's just written as the distance from the pivot, and the units are m. Easiest example to give you would be something like a spanner. You attach one end of a spanner to a nut, and the force you apply is at a certain, the spanner's length from the nut, and you're applying your force at 90 degrees to the spanner to get the object to turn. On to equilibrium. If the beam is in equilibrium, what that means is that the two torques either side of the fulcrum are balanced. That's where equilibrium comes from. It's equal. You see below we've got two forces, F1 and F2, pulling downward a distance of D1 and D2 either side of a support force Fs. At equilibrium, we're translationally. So vertical force is up and down. The force up must equal the force down, or the support force must equal the two forces that are either side of the fulcrum. Rotationally, so now we're looking at the torques. The clockwise torque, so the force trying to turn the seesaw round to the left or anti-clockwise, must equal the clockwise torque, which is the smaller of the masses F2 multiplied by the distance D2, which is trying to turn the beam clockwise or round to the right. At equilibrium, the anti-clockwise torques must equal the clockwise torque, so F1 D1 must equal F2 D2. At equilibrium, all the rotational forces and all the translational forces must be balanced. A bit like Newton's second law, if there's no unbalanced force, then there's no acceleration, there's no change in motion. So all vertical forces are balanced, all horizontal forces are balanced, and all clockwise torques and all anti-clockwise torques are equal to each other. So in the case of bridges, we have a beam here supported by two pivot forces, A and B, working vertically upwards, and we have a mass placed relatively close to A and slightly further from B, and a beam both providing a weight force downwards. If the beam is in equilibrium, we're going to have to look at how these forces will be in balance. So FA and FB upwards must equal FL and FB downwards. Now you'll notice the label for FB is in the middle of the beam where that point G is. Because the beam is what we call uniform, an equal amount of the mass is supported by A and B together. They share the mass of the beam. So in order to treat that mathematically, the distance that we use when calculating the torque provided by the beam is its mass multiplied by the acceleration due to gravity to work out the force, and we multiply that by the distance from the pivot to the middle of the beam. So we share the beam's length by each of the two pivots. So translationally, the two support forces upwards must equal the two weight forces downwards. So A and B force upward must equal L and beam downward. If we're going to look at rotational forces, we have to look at the rotational forces around one of the pivots. Let's say we want to work out the support force at B. We would have to make A our pivot. So we have anti-clockwise torques around or caused around the support force B are going to be equal to the support force B multiplied by the distance between the two pivots. Clockwise torques are going to be created around the fulcrum A, and they're going to be equal to the load of the weight multiplied by the distance from it to pivot A. Add that to the torque created by the beam, which is calculated by working out the force of the beam. So it's weight multiplied by the distance back to pivot A. If you pause the video now for a moment, you can read this little bit of spiel about the reasoning behind that equation. Just hopefully it will clarify a couple of bits for you. But I'm going to carry on to the next slide. So pause it if you need to have a read. As an example, let's just say we have a 20 kilogram wooden beam. It's 1.4 meters long and it has a 15 kilogram mass placed 0.25 meters from pivot A. The beam is supported at two ends, A and B. They are 1.2 meters apart. We're going to calculate the support force around pivot B. So for the beam to be at equilibrium, we're going to need to consider the vertical forces, and we're going to need to make the fulcrum pivot A. So in order to work out the support force at B, the fulcrum we will be measuring to is pivot A. Translationally, the upward forces provided by support force A and B must equal the weight of the beam and the weight of the load downward. Rotationally, we've got to make the two torques equal to each other. That means working out the anti-clockwise torque that is around force B. So we multiply, or we write down FB because that's the force we need to work out. And we're going to multiply it by the distance to pivot A. So that's the distance between the two pivots, not the distance between one end of the beam and the other. It's the distance between the two pivots. The next thing, the next part of that is to add to that the force of the beam. So that's the weight of the beam multiplied by half of its distance between the two pivots. So in this instance, 0.6 meters. So what we end up with as an equation is FB, because that's the unknown that we want to try and find out, multiplied by 1.2, the total distance between the two pivots. That's equal to the mass of the load multiplied by 9.8, the acceleration due to gravity, to work out its weight, multiplied by 0.25 meters, which is its distance to pivot A. We add to that the 20 times 9.8 for the weight of the beam, multiplied by the 0.6 meters, which is half of the distance between the two pivots, or where the distance between where the weight of the beam G is acting to pivot A. This gives us FB times 1.2 is equal to 36.75 at 117.6. So FB is equal to FB times 1.2 is equal to 154 times 154.35 newton meters. In order to find FB, we divide that 154.35 by 1.2 to get 128.6 newtons. I hope this has been of some use to you. Please be kind with your feedback. Take care.